7. That's a 30. And then from here we can divide by 5 to end up getting our 2x minus 7 is less than, I'm going to say, 6. And then from here we treat this the exact same way as we do as all of the ones that we've done here. Okay? You guys want me to finish that one off, or you guys think you're okay to finish it from here?
Yeah, we're good. We don't have
You're good? Is it good? All right. If there's any questions, again, even after the workshops, feel free to ask me, and I can answer your questions. All right? Okay. So that takes care of that. I want to go over super quick rational functions. Funny enough, like I mentioned last semester when I helped in this class, rational functions stayed as a topic or as a mastery topic throughout the whole semester. So our goal is to try to make that not happen again. So I kind of want to go over that. For rational functions, these are the 5 things that they ask for, right? I just want to make sure I'm not missing something. X-intercept, Y-intercept, vertical asymptote, horizontal asymptote, and when they remove this coming here.
I don't know if this counts as behavior.
And behavior. Okay, yeah, that's fine. Which is usually with this. Usually with the, I lied, it's usually with the horizontal asymptote. Because he wants it to be like as x goes to infinity, right? And y goes, yeah, okay, cool. Yeah, he has that notation he likes to do. Okay. We erase all this. So for the rational functions, the way that I like to kind of teach it is I'm just going to really describe how to find all of these pieces. And as usual, I'm just going to do it in example with you guys, and then I can just have you guys kind of figure out how things work out, right? So these are just going to be kind of like notes for now, in case you kind of want to see how we're going to solve all of them, right? So for x-intercept, the way that I usually tell, so for the x-intercept is you usually set y equal to 0, and then we solve for y, right? In practice, what this really means is that we're going to set the top equal to 0, and we're going to solve for the x values for that, right? So set the top to 0, then solve for x. That's going to be kind of how we solve for the x-intercepts. Y-intercepts is pretty similar in the sense that we set the x equal to 0. And then just solve for y. So these are the straightforward ones. It's the ones that I feel like you guys have been doing probably the longest. And again, don't get too confused on how I have my notes here. These are just going to be for us to have right now. I'll show you how this applies to the actual problems, all right?
No, I'm recording.
Vertical
Can you
asymptote.
understand the handwriting?
This is the one where we want to know. Oh, I think he also asked for range and domain, right? For this one? Yeah, okay. I'll just put those together. But anyways, vertical asymptote, we set the bottom equal to 0. And once again, just solve for the remaining, okay? So say solve for x. Now horizontal asymptote, I'll get back to that at the end of the first example, because that's the one that has a lot of different situations, and I just want us to figure these out first, and then at the end we'll just talk about horizontal asymptote as its own thing, right? And removable discontinuity, this is one where they tell you first you must factor, and once you factor, next step is cancel something out. And again, I'll show you some examples for all of these, so don't worry about it. Again, these are just going to be some notes so you know what's going on while we do the example. Okay. All right. Range and domain, we'll again talk about this because it's usually helpful to do this once we have a graph, right? So we're just going to go from there. So let me give you guys an example, and I'll show you how all this applies to my graph. Actually, I'll do it over here, actually, because more center for you guys. Okay, let me come up with the questions then. problems are going to be something along the lines of like graph, something like this, right? So before we start doing anything, we highly recommend to just start factoring. Right? For a lot of these things, we're going to have to factor to cancel things out. Factoring is just going to make our life way easier just to kind of solve all these things. So I guess, how comfortable are you guys with factoring? If I just give you this, is this something you guys can factor? Más o menos, kind of, maybe? You guys want me to just go over super quick trick about factoring? Alright. So, x squared minus 8x minus 15. So the way that I like to kind of teach factoring is using like the x method. Once you kind of get efficient with this, you're not going to need the x method anymore. But for now, it's just kind of good to kind of have. So some people call it the AB method. Some people call it the x method. They call it AB method because the term that goes up here is going to be the coefficient of your A times your C. So in this case, my A is just going to be 1, but that's not a big deal. And multiply it by 15, so I'm going to get a negative 15 right here. And down here, oh, I lied, this is AC and that's B, my bad. And then here is going to be my B term, so that's just going to be a negative 8. So once I have it set it up like this, the question becomes, what two numbers can I have such that if I multiply them, they're going to get me negative 15, but when I add them, they're going to give me a negative 8. So my recommendation for this is to let's just start to list numbers that multiply to 15. But there's a lot less of those than there are numbers that add up to 8. So give me any random two numbers that multiply to 15. 5 and 3. So 5 and 3, let's just keep these in mind. Is there a way to get 5 and 3 to get 8 from 5 and 3? Yeah, we can just kind of add them up, right? In this case, because it's a negative 8, I can just make, oh wait, that fucked up.
Yeah,
That wouldn't work, right?
yeah.
You're right. Because if I did like negative 3 and negative 5, that's going to give me negative 8, but it ain't going to give me this, right? So that's not going to work out. I might have messed up on my signs. Hold up. Give me a second. Yeah, I think I messed up. Sorry. That should have been a minus 2. Apologize for that, guys. So let's fix this up again. Sorry. So let's kind of do it the same way. So we got negative 2x minus 15, and we're still doing again the whole AC method, right? So AC is still going to be again this negative 15. B is going to be the one that switches to 2. So now I think this should work out a lot nicer. We did the 3 and the 5. Now this should work out, right? So if we're doing 3 and the 5, which one has to be negative and which has to be positive for this case?
Negative 5.
Negative 5. Positive 3. Do you guys see that?
Yeah.
Yeah, right? And we can always kind of check this, but yeah, we just know that negative 5 times 3, negative 15, negative 5 times 3, oh sorry, plus 3 would be negative 2. So what we do from here, the shortcut is if you don't have anything for A here, you can just go straight to whatever you have here to end up getting x minus 5 and then x plus 3, right? But if there's ever something here, so if there's like a 2 or if there's like a 3, basically if there's not a 1, you would have to split your B term into these two terms right here. And you're still gonna end up with that, but the steps, I guess the work is this. I'll show it to you. But again, if you're comfortable enough to just go from here to here, that's completely fine. I just want to show like what's the step that happens. So all I did right now is I replaced my B, my negative 2x, with the two numbers that we found on the left and the right. And now I'm just going to factor by grouping the first two and the last two. So in this case here, you see how I can take out an x from both of this? If I take out an x, I'm going to be left with a single one and then a minus 5, right? Not too bad. What about this one? See how I can take out a 3 for both of those? Take out a 3, now I'm left with an x minus 15. That's a line left with an x minus 5. And if these are the same, that's your first factor right there. And your second one is what we're left right here. So you see that? It's the exact same thing we got here. If you know the shortcut, then you can just go straight to it. But if you don't know it, that's how you always kind of get your answer. Right? Cool. So we factored that. So I'm going to put that on the top. X minus 5 and x plus 3. And just to kind of hurry this kind of up, did someone factor the bottom one? And does anyone have what it factors to? What's up?
X minus 5 and x plus 4.
Okay. So x minus 5, x plus 4. And again, and if anyone wants help factoring, you guys can ask me afterwards. And I'm more than happy to kind of help you guys out. Okay, so this is good. This is good. No problem. So let me write my new equation up here then, now that we have it set up. So the first step, like we said, was to factor, which was good. The next step should be just simplify as much as we can. What can we what can we simplify from right here? Or cancel out? X minus 5? Yeah, x minus 5 is seen in both of these, right? What's up? Is there a question?
Yeah, can you actually go over how you factor the denominator?
Sure. Yeah. No worries. Is it cool if I erase this? Okay. Actually, I'll keep this because it's a good example. I'll just do like years, if that's all right.
Yeah.
Okay. So let's see, x squared minus x minus 20, right? So the method that I like to use is, again, I'm just going to do the x. And up here is going to be my AC. In this case, my A is 1, right?
Yeah.
My B is a -1, and my C is a -20. Right, that's going to be my A, B, and C. So up here, I'm going to multiply my A and my C. So that's going to be just -20, right?
Yeah.
Not bad. The bottom one here is always going to be my B. And my B, I said it's just a -1,
Yeah.
so I'm going to slap it on right here. So the question again becomes, what two numbers can I get here and here to multiply to -20, but adds up to -1? And if you're ever confused and not know like where to start, just start by thinking of two numbers that multiply to 20. That's the
Right, I was
easier
thinking
way.
that, but I was like 20 and like I did -20. No, the multiply to -20, right?
That multiply to 20, yeah. So like I guess
10 and 2.
so 10 and 2. So just by looking at this though, is there ever a way to combine these to get 1? No, right? So we just ignore those. How about like another set of two numbers that multiply to 20?
Oh, 5 and 4.
5 and 4. There you go. And then you see how that's like a -1 right there, right?
Yeah.
Yeah. So I think making the list of the multiples, it's a lot easier just because you can cross them out super easy, right?
Mhm.
Yeah. So yeah, so then I'll just put it here. It'd be a -5 and a +4, right?
Yeah.
And then would you want me to finish it off too?
Oh no, I'm good.
You're good? Okay. Is everyone okay with just saying it's x minus 5, x plus 4? Cool. Alright, so let's go back here. So the next thing is going to be the factor, right? Or sorry, we factored to cancel things out. And we said that x minus 5 is what's going to get canceled out. So in this case, once we take this out, we're going to be left with an x plus 3 and an x plus 4. But this, what we canceled out, is going to be our removable discontinuity, right? So in other words, we need to solve what x value this is. It's pretty simple, it's going to be a 5. But in case you want the math for it, it's literally just going to be x minus 5, which is what we canceled. I'm just going to set that equal to 0 to see what x is going to be for that, right? In this case, like I said, it's easy. It's just going to be at x equals 5. So whenever I draw my graph, I'm going to have an open circle whenever x is 5. That's what the removal discontinuity is. Usually, again, it's like the first one you can kind of get without any issues. So that takes care of my removable discontinuity, and I'm done with that one. Okay, so just to kind of recap, the function that I'm looking at now is going to be this one, right? I factored it, and I've canceled as much as I can. That is in its simplest form, and now we can work on it. So let's start with the x-intercept. So the x-intercept, the easiest way that I always say is just at the top, just equal to 0, right? I did say that you set y equal to 0, so it's kind of like saying this, right? I said you set the whole thing, so y, we set that equal to 0. But what happens when I multiply my denominator on both sides? X plus 4 on both sides. Just kind of cancels out, right? If I go x plus 4 on this side, that's gone. And if I multiply it by 0, well, what's x plus 4 times 0? It's just 0, right? So that's why you're left with only x plus 3 at the top, which is why I said technically you set y equal to 0, but in all the examples, it's always going to end up just being the top, setting to 0. So once you know that, you can always just go straight to setting the top equal to 0, right? So in that case, what's my x value going to be here? -3, right? Yeah. You get -3. So my x-intercept is going to be at -3. That's all it's saying. This is going to be at x equals -3, right? What about my y-intercept? Y-intercept arguably is easier because all we have to do is we set all of our x's to 0 and we just simplify, right? So for this one, if this is my equation, my y-intercept is going to be just 0 plus 3 over 0 plus 4. Again, all I did is all I'm doing is I'm plugging in 0 for my x's, right? So what's my y going to be in this case? 3/5 or 3/4? 3/4, right? Okay. Yeah, 3/4. So my y-intercept is going to happen at y equals 3/4, right here. So we got the x-intercept, we got the y-intercept, we got the removal discontinuity. Now we're really just looking for the asymptotes, right? So the vertical asymptote is arguably, again, the easy one because we just want to set the bottom equal to 0. And the only reason we're doing that is because the vertical asymptote is just asking us when do we have an error in our function. And usually, we're not allowed to have a 0 in the denominator, right? So by making the bottom equal to 0, that's going to tell us exactly where that error happens. So for vertical asymptote, I'm going to set the bottom equal to 0, which just means I'm going to grab my bottom and again set that equal to 0. Right. Easy peasy, that's just going to be what, -4? Right? So my vertical asymptote is just going to be at x equals -4. And again, I'm just collecting all this information. Once I have this all together, then I'm going to put it all into a graph, right? So I'm just kind of working on all this right now. Okay, so now we get to the horizontal asymptote, and you'll kind of see why I kind of went into the last minute, or last, I guess, section to it. Because it's probably the hardest one, and it's the one that you are going to have to memorize it to some degree, right? With all of these, you can always count on these like methods to find them. Horizontal asymptotes, you're going to have to remember 3 different methods, all right? So, I guess I'll do it closer to the middle since we're here. I'm going to erase this part here, but I'm going to keep the top, right? So, horizontal asymptote. This is going to be its own little thing. So, for horizontal asymptote, before we even start, what we want to start looking at is the highest exponent on both the top or the bottom, right? So that's what we want to kind of look at, the highest exponent for both the top and the bottom. So the first situation is if I gave you something along the lines of this. Okay. So in this situation, my highest exponent for my numerator is a 2, right? My highest exponent for the bottom is also a 2. So in this situation, where they're both the same, my horizontal asymptote is going to be the value of the coefficients of your x's with the highest degree, right? So in other words, it's going to be like y equals 5 over 8. And this always works as long as they're both the same, right? So again, just for like a random example, I can have something like 10x minus 7x squared over, let's say, 10x squared minus 2. My highest power here is a 2, and my highest power here is a 2, so it's the same. So in this case, my horizontal asymptote should be a -7 over 10. Does that make sense? Don't get confused with like if it's not in the front. We're paying attention to the highest exponent, right? Does that example make sense here? How it's a -7 over 10?
Mm-hmm.
Cool. Okay. So, second example is going to be, what if the top is bigger, right? So what if I have something like, let's say 5x cubed minus 10 over, just say 8x minus 1. In this case, my exponent at the top, or my highest exponent is 3 at the top, and my highest exponent at the bottom is 1. So the top is bigger, right? If that's the case, we have no horizontal asymptote. We just don't have any, right? That's the second situation. Third situation, like you guys probably figured out, is what if the bottom is bigger, right? So what if I have something along the lines of 5x cubed at the bottom, and at the top I guess I had a 5x minus 1. So again, the cube is at the bottom, which is bigger than just a single 1, right? So the bottom is bigger. If the bottom is bigger, your horizontal asymptote is always going to be at y equals 0. Now this does not mean that these are the same, right? This means you don't have any horizontal asymptote. And this means your horizontal asymptote is at the x-axis right here. That's a common mistake I see a lot of people doing, that if they see y equals 0, they automatically assume it means no horizontal asymptote. But you gotta remember that means it is there, it's just at 0, right? So these are the three situations we have. So if they're the same, we just take the ratio, essentially the fraction of the ones that have the highest exponents. If your highest exponent's at the top, we just forget about horizontal asymptotes because we don't have any. And if the bottom has the highest exponent, we automatically just know it's always going to be y is equal to 1. Right? So these are the three situations we have. So looking at those, and looking at the equation we have here, what situation are we in? 1, 2, or 3? 1? Yeah, right? Because what's my highest exponent in x plus 3? Well, it's just a 1, right? How about for x plus 4? It's literally just 1. So if they're both the same, all I gotta do is grab my number in the front of this one, which is just gonna be a 1, and my number that's in front of here, which is just a 1. 1 over 1, so what's my horizontal asymptote gonna be? It's gonna be 1. So my horizontal asymptote, y equals 1. And we're done with that one. Funny enough, the end behaviors are gonna go based on the horizontal asymptotes, because the horizontal asymptotes, as you guys know, it's the one that as you approach, you get closer and closer, but you never touch it, right? So we know it's gonna go something along the lines of like that. So horizontal asymptotes is what really helps you find the end behavior as well. Okay, so we got all this information, but the problem's probably gonna ask you to graph this whole thing, right? So this is where we have to put everything together just to kind of see what our picture's gonna look like, alright? So could I erase all of this? Is that cool with everyone? So now it's time to actually graph this thing here. So we should probably start with the x and the y intercepts. That's probably going to be the easiest things, right? So I'm saying that my x-intercept is at -3. That's going to be the easy one. Apply that at -3, and I'm done with my x-intercept. This is done. Y-intercept, it says it's about, is that 3/4? 3/4, right? Yeah. So it's going to be, if that's 1, it's going to be about here. It's an approximation again, so no worries, but that means we're done. Now, vertical asymptotes, we have one where it says x is -4, right? Well, all that means is we're going to go here, have that asymptote at -4. That takes care of that. Last but not least, we have the horizontal asymptote, and that's the one that we solved that it was just going to be at y equals 1, right? What's up?
I don't know if this is like, Professor Rhodes told us that the horizontal asymptote only affects like the outside, so everything past the vertical asymptote and the x-intercept, so that like that line in the middle would be there.
That is completely true. You're right. Horizontal asymptote does only affect the outsides. So some teachers do write the whole thing. Rhodes is one of the ones that he doesn't include in the middle. So yeah, you could just get rid of it, but with the thought in mind that we do have it at the end. But yeah, that's right. Yeah. So yeah, so I guess I'll just kind of keep it over here though, because I believe it's gonna end here. I like to just draw it over the whole thing, with the understanding that if it's in the middle, you can cross it. But again, it's the same thing. So from here, we have the general shape because we know it's gonna go, or actually I should make this up. So from here, we have the asymptote, we have some points, but we don't have like the actual, I guess, shape of it, right? Because for example, on the left side here, I could either be coming from here, or I could be coming from up here. It all really just kind of depends, right? Easiest way if you're ever in doubt is really just gonna be to plug in a number in that section. So you see how this is a -4? So what number can I plug in to kind of test something on the left side?
-5.
-5. So let's try that out. Let's plug in a -5 to this one. What am I gonna get?
-1. So it's positive.
That's a 2, right? So that's gonna be up here. And because my asymptote's gonna be right here, I know that the pattern from here is gonna be just in this direction. Does that make sense how I made that assumption like that? The other way that I know it's gonna be up there is I can't go down here because there isn't any x-intercepts to kind of hit, right? So I know I'm not allowed to touch my x-axis on this side. So just by that, I know it's gonna have to be going up. Did that kind of line of reasoning make sense? Kind of. I guess when in doubt, again, we can always just plug in another, like -6, and you'll kind of see that it's going to be a point here. But that you should be kind of starting to see patterns just by looking at the asymptotes and the x-intercepts. So I'm just going to try to repeat what I said, such that I know that I can't be going down here like this. Actually, I'll do it in a separate color. I'll do it in black. I know that I can't be going this way, like this, because if I go this direction, you see how I pass by the x-axis right here? But what's my only x-intercept? I only have one that's going to be here at -3, right? So if I go in this direction, I'm passing the x-intercept, but I don't have another x-intercept to use. That's why I know it can't be this black line. It has to be going up and not touch the x-intercept. So hopefully that makes a little sense how I make that, or do you want me to clarify a little differently? Is it good with that? Alright. Okay. So then we got on this side. So with some experience, again, you'll kind of see that you know it's not going to come down from this side because of the y-intercept or the x-intercept that we have and the y-intercept that we got over here. So just by kind of eyeballing it, you can kind of assume it's going to go like this and just keep going. But again, if we're ever not sure, we're always allowed just to plug in a number just to be safe, right? So what number do we want to plug in? Let's say that we don't know that it has that shape. So what can we plug in to find out?
-1.
Let's plug in -1. That's a good one because we know it's going to be somewhere here in the middle. So what's that going to give me then if I plug in like a -1?
2/3.
2/3. So that's going to be somewhere even lower over here, right? So you kind of see that already? You see how it's going to kind of come around from there? So we got with these 3 points, it should be kind of clear. Then our graph is going to look something along the lines like that, right? I kind of extended it kind of far over here, but yeah, that's kind of how it goes down, right? So we have the asymptotes that crosses over here. Again, in this example, nothing crossed it. We have another one over here, and that's kind of our graph right there. Again, I think it's important to start with your y-intercept, your asymptotes, and then from there, if you're not comfortable with just the general shapes of these, I think just plugging in should probably be the best bet, right? What's up?
If there's no removable discontinuity, can you just plug it back into the original equation?
I forgot to remove the discontinuity actually, so I'm not done yet. Yeah.
But if there isn't, you can just plug the numbers into the original equation.
Yes.
Yeah.
Yes. Yeah. So I actually forgot about the discontinuity. So thank you for bringing that up. So the discontinuity is probably the easiest thing to draw because all it's saying is that whenever my x is 5, I'm gonna have a hole. That's it. So if I go to 5, 1, 2, 3, 4, 5, all I'm saying is that right here at 5, I have a hole. That's literally all the discontinuity is, right? Everything else is the same. Just make a hole there. So that's kind of like an overview of rational functions. Any questions about how to find any specific parts? Any questions of specific situations that you might have seen that might be harder? now? You guys are chilling? Okay. So it is 450. Would you want me to give you an example that you can work on if you want, or do you want to put something else? What's up?
I have one question.
Yeah.
If, like, for example, on the top, the numerator is negative x squared.
Negative x squared. So something like this.
Yeah.
Yeah.
Does that change the shape of any of the graphs, or will it only change, like, the horizontal asymptote to the
I think that's gonna change it. Yeah. So I think that would change your y-intercept, and I believe it wouldn't flip your. Yeah, because I think your y-intercept will all of a sudden be negative, and your asymptotes might also be on the negative side as well. So we might actually be going this way and then that way for that. Yeah. You want me to do it after you, or do you just kind of?
I think that would be.
Okay. Okay. Any clarifying questions? Should I go over something else, or you want me to give you a slightly different problem with this kind of stuff?
Can we do identities?
Do identities? Okay. So everyone okay with this for now then?
Yeah.
Okay. Identities. These were the trig identities, right?
Yeah.
Alright. Okay. So I guess quick question: has Rose asked you guys to learn the unit circle already?
Yeah.
Like tell you guys to memorize it, learn it.
Yeah.
Like you guys got another level. You like put it back to your hands.
Yeah.
Okay. So hopefully you guys are spending some time on it, because that's definitely going to be a huge helping hand for the trig section. And I do mean like this whole for this whole trig section, that's going to be like the big thing to help you out. So.
Thank you.
Hey, you guys take care. Good luck in your exam tomorrow. Good luck. Good luck. Okay. So we're doing trig.
Oh yeah, here. You honestly bring it up to the front.
Okay. You want me to list out the ones that are important to use, and then kind of go from there for them? Because I know he's asking part of the. I think like the homework problems was like, if they give you like secant of something in quadrant something, find the rest or something like that, right? That's the kind of stuff you guys are doing, or no?
Yeah.
Okay. So I guess I'll give you the list of the important identities. Let me know if I include one that he hasn't gone over, because I know he's gonna go over like a lot of them, but I just want to make sure I'm keeping with what he's teaching you guys.
Yeah.
So the Pythagorean identity is probably going to be like the big one. This is one you're gonna have to just like know. As in, even in future classes, you're expected to just kind of know. Like in future classes, you're expected to just have that like in the back of your mind as well. Sine squared plus cosine squared is equal to 1. Right? The other ones that kind of come along with that, but that all derive from this one, is going to be the tangent 1 equals to secant squared of this, I believe it's right. Yeah, like that. Alright, that's the other one that's going to be kind of common. Though again, they do derive from this top one. Do you guys know about the reciprocal ones, like sine and how it corresponds with like either cosecant, secant, all that stuff? Are you guys familiar with that already? Kind of? Okay, let's go over that, because that's also going to be important. So, sine, cosine, and tangent, right? These are going to be like the big three that you're going to have to just know. And we work often with the other ones that are like cosecant, secant, and cotangent, right? And so I like to associate each trig function with its I like to correspond the trig function with, no. Basically from the 3 other trig functions, we can always correspond them to one of these 3. So sine is going to correspond with cosecant with theta, cosine is going to correspond with secant with theta, and tangent is going to correspond with cotangent that. And all I really mean by this, which is I think you guys already know, is that cosecant is the same thing as like 1 over the sine, right? Secant is the same thing as 1 over cosine, and tangent is the same thing as 1 over 1 over tangent. What's important to kind of associate these together is going to be the sine goes with the cosecant, not with the secant. That's a common mistake that people make because, you know, they both start with s's. They try to correspond these with each other, but it's not. This is the s with the c and the c with an s. Right? That's I always try to remember it for myself, and it kind of helped. So anytime you're working with anything in terms of like cosecant or even secant, you can always write it in terms of like sine and cosine. And usually sine and cosine are the easier ones to work with, right? So that's what we kind of want to work with those. Okay. I don't think he's gone over like the sum formulas and all that stuff with you guys, right? Yeah, like the whole cosine of like a plus b, that kind of stuff. I'm assuming he hasn't gone over that, right? Yeah, that's probably something you'll see afterwards. So that's good. Are there other identities that they go through? These are kind of the big ones, right?
Just those 6.
Just those?
Yeah.
Wait, you're forgetting one.
Which one am I forgetting?
The cotangent one? Cotangent squared plus 1 is equal to.
There's one more for the top ones.
Yeah, for the Pythagorean one, right? Yeah, that's the cotangent one, I think.
Yeah.
The 1 plus cotangent.
Squared.
I didn't include this one just because I think this is number
Cosecant. Cosecant, you're right.
Okay.
Yeah.
I didn't include that one. I just want to make sure.
I think it's squared there.
You're right. It's squared.
Yeah, okay. I thought so too.
Squared. So I didn't include this one because it's not often used. These two are the ones that are mainly used, and from these two, this is the one that's mainly used. But yeah, I guess it is good to know all 3 of them like that. But yeah, I do recommend definitely this one, potentially this one, the 3rd one I guess you guys time. But yeah. So yeah, man, no problem. Okay, do you want to go over some of the homework problems that ask for this kind of stuff? Okay, so I was looking at one that I kind of mentioned where it was like, they give you like, like secant this, find sine, tangent, and all that stuff, right? Is that the kind of stuff you guys want to do for that?
Yeah, because usually the problem will be like, if sine of theta is equal to something, and theta is in this quadrant, then what is like cosine? What is all the rest? Yeah.
Yeah, okay. Let me find an example, and what's actually, I think I did one. That's fine, I'll just find an example. Yeah, right here. No, that's half. Yes. Dude, I seriously have this right. Okay, I'll make my own one then. Okay, so let's say, yeah. So it's kind of like saying this. Let sine theta equal to, we'll say it's a -4/3 for now. And we're going to be in quadrants, let's say quadrant 2. And the goal is to find all the other ones, right? So that's going to be, I guess I'll put it. Yeah. The goal is just to kind of find like cosine, tangent, secant, cosecant, and cotangent, right? And we have to use these kind of identities to kind of figure that out, right? This is where the Pythagorean identities is going to be super helpful because we know one of these variables pretty much at all times, anytime they give you this kind of information, right? So they tell us that sine of theta is going to be -4/3. So if we just use this, what we got, we can literally just plug it in for sine and then kind of solve for cosine, right? So let's do that. So I'm just gonna do negative 4 over 3. That's gonna be squared. And I'm gonna add a cosine squared theta and make that equal to 1. So the goal right now is just to solve the cosine. This is gonna be like an algebra kind of problem, right? So how do we solve this one?
Square the
Good.
negative 4 and 3.
So that'd be what, 16 over 9, I think, right? Alright. Subtract to the other side.
Oh yeah.
Right. So that's going to be cosine squared theta. I can show my work if you guys want, but I believe that's going to be
16 plus 9.
negative 7. Actually, yeah, I'll show my work. Yeah, negative 7. Alright. I'm not tripping, right? It's negative 7.
So it's 1 minus 16 over 9, right?
So 9 over 9 minus 16 over 9.
Yeah.
So that would be 9 minus 16. I believe that would be a negative 7.
Yeah.
So negative 7 over 9. So this is nice. So what's my last step to find cosine then?
Square root.
So square root both sides. And cosine, I sadly got a negative, okay, so my example probably not the best, but let's keep going. Oh wait, yeah, let's make this a positive, just to make our lives a little easier. So that would be a 7 over 9. That's something that's going to change for that. So how do we solve this though? Square root of 7 over square root of 9. Anytime we have a square root, we should split it up for the top and the bottom. So that's going to be root 7 over root 9. And we do it separately like that, and we can just solve them, right? Okay. So what is cosine going to simplify to? So the top, I'm just going to tell you, it's going to stay as negative 7. That's not going to change. But what about the bottom? What's the square root of 9 going to be? 3, right? Yeah. So I know my answer for root or for cosine is going to be just root 7 over 3. And that's awesome. That's my first answer right there. So I'm going to write it here. Sine started off with 4 over 3. I found that cosine is root 7 over 3. That's what I just found. Okay. I'm going to erase this part real quick to go over to the next section. So, I'm sure that's good. Okay. So, this is the problem, right? We're trying to find all of these 6 trig functions. We have sine and cosine. So just by looking at that, I can find cosecant and secant super easy. Right? And we're going to be using these properties, but the way we apply them is literally like one of the easiest things we can do, right? So if sine of theta is equal to 4 over 3, I can find cosecant, which remember, it's the one that corresponds with sine, literally just by flipping my fraction. That's all it's really asking for. So what's my cosecant going to be then? 3 over 4. I can show you how that happens too if you want. So I know my sine is equal to like a 1 over, or what is it? We have cosecant is equal to 1 over sine, right? Which is the same thing as sine being equal to 1 over cosecant. And so all we're doing, and all that we're doing is that because it's in the denominator here, we're dividing it, which means we're just going to divide by a fraction, which means we're just flipping, right? So, though I guess to show you that you end up with this, if my sine is equal to 4 over 3, and I'm looking for cosecant, you see how I can like cross multiply to get 4 cosecant is equal to 3, and then I just divide by 4, and that's how I end up with that. So you can do it out, and you get the same thing. But with practice, you'll see that it's literally just going to be flipping the fraction. What's up?
I have a question for your first step in sine squared plus cosine squared is equal to 1.
Yeah.
You made you inserted that's what I was wondering.
Sorry, yeah.
Is a
Should be
but then
fine.
that should not change the answer, right?
No.
Because you square it anyways.
Exactly.
Okay, for
Yeah,
sure.
yeah.
Okay.
My bad about that.
Okay.
But yeah, so off of that, if I know my sine is 4/3, I can solve pretty quickly that cosecant then it's just going to be 3/4. So cosecant 3/4. What about my secant then? My secant corresponds with cosine, right? So I can do the same thing. So what's going to be my secant? What's going to be my answer? Three root 7 over wait, 3 root 7 like that? Right?
I did it like the root 7 over 3 and that was flipped. So it was like 3 over root 7 and multiplied it.
Yes, I think you're already solving it. Yeah. So I'll solve it super quick and let's just make sure that we get the same thing, right? So yeah, so the first step is to flip it like this, but the issue is that we don't want this square root at the bottom. So that's when we rationalize it. And that just means to multiply the bottom by the square root of whatever we're trying to fix, right? So multiplying both top and the bottom by root 7. And that should give me 3 root 7. That doesn't get simplified, we just keep it like that. The bottom, however, anytime we multiply 2 square roots like that, they're gone. Or if the answer is the same, the square roots are gone. So this is what you end up getting, 3 root 7 over 7, perfect, cool. That's exactly it. That's gonna be my secant. That step makes sense right here?
Yeah.
Cool. Alright, so that's my secant, so I'm gonna slap it in right here. Over 7. Alright, so now all we're missing right now is tangent and cotangent. So cotangent, I'm not even going to think about that right now, because cotangent is corresponding with tan, so I just want to focus on tangent right now, right? So does anyone have an idea of how we can do tangent? Yes. Exactly. So another property that, I guess it's a property that people take for granted because it's just something that's usually how we define tangent, is literally just going to be sine of theta over cosine of theta. This is great because we already have sine of theta and we have cosine of theta. So all we got to do here is just kind of plug them into where they belong. So let's do that. Sine of theta is what, 4/3? So we do 4/3 over here. And what's cosine of theta going to be? What's up there? Cosine of theta I got to be root 7
over 3.
over 3. Alright. So who's uncomfortable dealing with fractions inside of fractions like this? I know some people find this kind of ugly. You guys seem pretty good with this or not? You good with this? You good with this? You good with that? Alright. So I don't have to show you guys, this is the same thing, it's just 4 over root 7 then, which would be 4 root 7 over 7. I skipped a few steps just because, but do you guys want me to show you how I got there?
You just multiply the top and bottom by 3.
Yeah. So first step, yeah, was just multiply by 3. That's gone. That's gone. I'm left with 4 over negative, or 4 over root 7. And once again, like we did there, we just rationalize it. Right? That's how we do that. So we found our tangent. It's going to be that. So I'm just going to put it right here. 4 root 7 over 7. And then similarly, what about cotangent? What's that going to be? What's up?
I have a question for the where you do you take the square root of cosine squared of theta, and then
Like
right there, should that be plus and minus, or no?
You are completely right. You are actually right. I actually forgot about this. But we stick with one of the answers. because we're in quadrant 2.
Yeah.
So actually, is cosine negative or positive in quadrant 2?
Its cosine is x negative, so x is negative.
Negative. So you're right. So this actually has to be a negative cosine. Good catch on that one.
Okay.
Which means which one of other these have to be negative?
Secant.
Secant, because that's the one that corresponds to cosine, right?
Mhm.
So that one also has to be a negative. Good catch on that one, man. Because our sine is positive because we're on the second quadrant,
Mhm.
and therefore cosecant is also positive.
Mhm.
So yeah. Thanks for that, man.
Okay.
Did that make sense, I guess, for the other two? Or do you want me to explain that
for
real quick?
this, well, it's kind of just like looking at quadrant, right?
Yeah.
Yeah.
Yeah, it's
Just
kind of like,
depending on which quadrant.
yeah, it's kind of that whole, I think Rhodes does the all calculus, or all students love calculus, I think. I just remember the whole plus and plus, minus minus, and then minus plus, and plus minus. I just remember the signs, but I know some people have some tricks to kind of remember. But that's what we're looking at, exactly. So we're looking at quadrant 2. We know that my cosine has to be negative, and my sine is positive. So yeah.
Yeah.
If I had done like quadrant 3, obviously then we have to change some other ones as well, right? Great. Thank you again for that, man.
Mhm.
And so, oh yeah, for cotangent, things we talked about. Did everyone, or did you guys get cotangent? Or not yet?
No.
So it's
This is kicking my ass.
I can tell, man.
I'm on number 8, still getting my ass kicked.
How long the homework is what, like 20 problems?
35 problems.
Yeah, okay, never mind. Sure. Do next week?
Huh?
Do next week?
No, I have to finish. I don't want
Wait, what?
to.
Oh, God. Alright, anyways.
Some of it.
Cotangent, did we get it? Any ideas? You still want me to do it?
That's cool. No, wait. Was it?
Cotangent.
Oh, I got it. Yeah.
You just flip it, right?
Yeah, just flip it. So for cotangent, it's gonna be, we can start off with just 7 and 4 root 7,
Seven.
and we can always just kind of rationalize this like that.
Mhm.
Alternatively, if it's easier, what you can try to do, again, this is just it, if it's easier. We can write cotangent kind of the same way that we did tangent, but we know it's going to be flipped, right? So this is going to be our cosine, and this is going to be our sine. And so we can go in this form to see what it's going to be. It's going to get you the same answer, but again, it just depends what you're more comfortable with. If you already have tangent, you can just flip it. If you just want to do it directly, you could do cosine over sine.
Yeah. Okay.
So I think if you guys were to rationalize it, I think you guys get something like this. Right? And I think you should get the exact same thing if you do it this way too. Which I can actually just show. So cos actually I have right here. 3 is the bottom would be 4 3. And this would just be cancel out and the left with, yeah, perfect. Right there. Exactly.
Go for the Mhm.
Just put your name on it just to kind of
Sine is y. Sine is your y value.
Put my name on where?
the textbook thing.
Okay.
Yeah, just
Aha,
put your
aha.
first name and then just put
And then cosine is the
Yeah.
x value, so it'd be the x-axis. Yeah.
Does it make sense?
Yeah.
Any questions on how we get this? Something like that? You good with it? You guys want me to give you like another example? You guys can try this one on your own, or you guys want to call it here? It's up to you guys. I can also do another section. I can do other problems, things like that. Just let me know. You good?